In this final video, we're going to discuss a physics concept, work. Okay, and if you start singing the work song by Rihanna in your head, that's okay too, because you are going to do some work. Haha. Anyway, from physics, we define work as force times distance, but that has certain assumptions with it. That is true if we are on a straight line motion with no incline and we're moving the object from point A to point B and the force is constant. Okay, so that would be like pushing a box along a flat ground and with a constant rate of force. But that doesn't happen all the time, right? Like sometimes you might be moving, you'll see that later in the video, and you need to push things down ramps or up ramps and that sort of thing. And so here, when we have these cases, d is going to be a displacement vector. It does have a magnitude and it does have a direction. The direction just has an incline to it or something like that. But still, we're moving it in along a straight line from point A to B, and we assume the force is constant too. The force, again, we think of that as a magnitude and direction as well, which may or may not align with the direction of displacement. Okay, then the work done, oops, typo, is given by F dot D. That is the dot product. And we know from our definition dot product that if we do F dot D, that's the same as the product of the magnitudes times cosine of the angle in between. Okay, so there we go. First example, okay. I want you to pause video, read it, and take a shot at it before actually watching the solution. Okay, so the idea is that we have a doggy. I'm going to represent the dog as a little blob here. Okay, so here's the blob, because I can draw but not dogs. And we want to pull a sled. Okay, so here's the sled. I'm going to use it as a point. And so we're pulling the sled in this direction, and horizontal path 200 feet is how far it's going to move. And actually, so the dog is a little bit bigger of a blob. Okay, and it pulls the sled at an angle of 15 degrees from the horizontal. Okay, and this is pulling at 25 pounds. Okay, so we want to find the work done. Well, work is force dot distance, right? Now, I could represent each of these in component form, okay, and I'm going to do it two ways. It so happens that it's easier to do it one way rather than the other. Okay, when we do the force vector, we would say, okay, well, it's going to be this force, right, is going to be 25 cosine of 15 degrees and 25 sine of 15 degrees. And then we dot that with the displacement vector, which is just going to be 200, 0. Okay, because again, you're going 200 in the x direction, nowhere in the y direction. Okay, so then at the end of the day, I end up with let's see, 2 times 25 is 50, and then we need to add 2 zeros, so 5,000, if I'm doing my math right, off the top of my head, cosine of 15. I need to check this now. 25 times 200, yep, 5,000, okay. And so then we do that times cosine 15, and I get, this would be 4829.6-ish. The units here would be foot pounds. Okay, so that's one way of doing it. Now, I'm going to do it a different way that doesn't involve representing it in vectors, and that's just work is magnitude of the force times magnitude of the displacement vector times cosine of the angle in between them. Well, my friends, that is the same as the magnitude of force is 25, the magnitude of distance of the displacement vector is 200, rather, not 500, 200, and then I multiply by cosine of 15 degrees. Erase 15 degrees. Okay, so wait, isn't that the same as 5,000 cosine 15? Yep, it is, so I get the same exact answer. Okay, so just another way of looking at the problem and setting it up. Okay, And I should say, I should do a nice lovely sentence, and then 15 years later I finished the problem. Okay. Now, for this other one, I want you to pause the video and try it out. When you're ready, resume the video to view the solution. And so here's the solution that I have. Nice little picture to begin with. The 300 actually ends up being completely irrelevant in the problem. So you're welcome. But the idea is that we're pushing down now, kind of. At a diagonal, applying 150 newtons of force. Newtons is just another unit of force, just like pounds is a unit of force. And so then we are applying that at an angle of 25 degrees, and we're moving it 8 meters across the room. Okay, so then if you want to look at it that way, you can, or if you want to translate this to like a Cartesian coordinate system, this would be your setup. D would be going completely horizontal, and then F is 25 degrees from the horizontal. Okay, and consequently, with that representation, we can represent F in terms of its direction and magnitude. Okay, and then computing work, again, you can do it in two ways. You can use the dot product definition, write out the two vectors, dot them, and then multiply the components respectively. Or you can do magnitude times product of the magnitude times cosine of theta, and either way, you get the same answer. Okay, so you'll get some practice with these types of problems in class. Have fun, enjoy, and this is your last video.